And for the next speaker, I would like to invite Henrik Hulgaard, who is our CTO and founder of Configit. And Henrik will be covering a presentation regarding how to reduce complexity and increase engineering productivity through configuration lifecycle management. Henrik is in the studio, so welcome, Henrik.
Thank you so much, Shahid.
So if you take my place and then you can take on.
Good afternoon, everybody. It's a pleasure to be here. What I will try to introduce to you in this session is how a CLM solution can help engineers in their work. It's not necessarily an additional burden to deal with. So when we talk about CLM, we talk about making sure that the different functions are aligned, that there's a single source of truth when it comes to the offering, and that sort of enables all these benefits that we see, where making sure that what we can design and build is also what we sell and can manufacture and eventually can deploy and service. In the center of the CLM diagram here, we have the concept of modeling, and modeling for us is the center of what we do. That is where you create these product models that define the variability of the products. And that is the key activity to enable this alignment. So the foundation of doing a model is called features, or we call them features. Sometimes they're called characteristics and values and options and option groups, but we call them features and feature families. And this is a abstraction above the parts. This feature is the language we use to express the variance that we can build. So an example of a feature could be the color of a car, red, green, blue, and clearly that choice is affecting the parts on the car, but it's not a part in itself. And when we look at the features, we often group them in different types of features. We can have those that are highly technical. If it was a car, it could be the frequency that our key is communicating with the car. We have the more marketing features. Those could be things like packaging things up, package information, and grouping, and making also features that you might expose in a sales process that are more oriented toward the customer. And the sales features are these, can be sort of really the requirements coming from the customer. We typically have these features in a global dictionary, so all different products, they share the same codes. This is quite basic, but also quite essential to make sure that the models that we build all have a shared vocabulary, that they use the same codes, basically. And when we have these features, we create the models, and based on those models, we can then do a configuration of the product, and that configuration will then, in the end, create what we call a feature string, the feature string being the collection of all the features, both technical features, commercial features, and from that DNA of the product, we can then derive a number of different types of information, and very typically, one of the pieces of information we would like to derive from this feature string is the bill of material. Now, as you can see, there is this layering on the product. So at the bottom, we have the individual parts and assemblies that are the physical elements that make up the product. They get organized within the bill of material. The bill of material will have variability in it. It will be a super BOM when it's a configurable product. And on top of that, we have the features, and the features then are being used in the product models. So that's sort of the hierarchy as we see. And we deal with the green area here. We deal with, when we say the modeling in the center of this CLM circle, that is the features and the models. So where do these models come from? Where do the rules come from? Well, the rules come from the engineering aspect of the product. What is technical possible? Can we have that feature together with that feature? If I choose that, I cannot have that, or I must have that. That, from a purely engineering perspective, will it work? Then you can allow it. If it will not work, you have to put rules in to disallow it. And on top of that, there is additional rules I should say in the engineering space, there's also legal rules that you may have that dictates from wherever your product is going to be sold. You might also have some legal rules that says that in Denmark you must have this capability or are not allowed to have that capability. That would also go in the engineering space. But then in the sales area, that's much more on the commercial side. What features are we going to offer in the different markets? What are the options that we will make standard and optional and maybe not allow? We might package things up. And all these rules combined is what makes up the model that can create these feature strings. And as we just saw, a typical system landscape will consist of different systems. It will consist of, in this diagram I showed Configit ACE, it will be the modeling environment where you define these product models. You have the configuration engine that can generate the feature string. That's in the green area on the top left. That is integrated to the PLM system because the configurable bill of material will normally sit in the PLM system. And within PLM is where you define your engineering BOM and you map that to the manufacturing BOM. And at some point that is being synchronized down to the manufacturing system, the ERP system, where it gets combined with the configuration that comes from the sales processes, whether that is a sales tool or a dealer portal or whatever it might be in this CRM, CPQ area. The orders come in with the configuration, gets combined with the configurable BOM, and that is then what is the BOM that you need to produce and deliver. That's a very typical system setup. And of course, you can zoom into this and start discussing exactly what elements are mastered in what systems and how are these arrows actually going to look like. There are two key processes in this diagram. There's sort of the engineering process, the product definition, and there's the more transactional process, which is the order to delivery process. The key point here is that the language that these integrations are using are all features. They are not parts. So when you configure the product, you're configuring based on features, not on parts. When you synchronize the information to the PLM system, it's all about what are the combinations of features that we will allow on a particular product. We can zoom in and the speaker later today, Anders Rasmussen, will actually spend his entire presentation on exactly this picture. So I will not go into the details, but there is this triangle or shape where you have the parts and the bill of materials at the bottom, and then you have layers of rules on top of that. And how that interplay is when you have part of this diagram is sitting in PLM and another part is sitting outside PLM in ACE, for example, in a CLM system, there is an interplay. And a typical question, of course, is how does that work? And doesn't this just make life harder from the engineering perspective? Because now we have two systems where we have to deal with stuff, and we have to make sure that these two systems are aligned. And the short answer is, I actually think this will make life much easier for engineers. And I'll try to illustrate that with a few cases here today. So you could also ask the question, why do we even need another system? Why can't PLM do it all? That's a question I've heard actually quite often in engineering areas where they work with their PLM, they do all the work in PLM. They cannot really understand why do we need to move outside of PLM, in particular because most of the modern PLM systems out there are capable of defining features and rules. So why do we need to have another system? I put on here a typical PLM circle. You will see that it resembles quite closely the CLM circle that we normally use. You have the design and the manufacturing and the service. What I always find interesting is that from a PLM perspective, they tend to forget the whole sales process. So they tend to forget how the information from PLM is being used in sales applications to guide a user to make the right choices. And I just picked a random diagram here found on the internet, but this is actually the case if you go to most PLM vendors. They tend to ignore the whole sales area. But that's not the only reason why we need another system to link from PLM to sales. There are actually other good reasons why PLM is not good enough when it comes to authoring of rules. One point is that the rules that we deal with are not just engineering rules. And there's a lot of reasons why adding all the commercial stuff within the PLM system from an engineering perspective, that is looked at as just making their world much more cluttered and unnecessarily so, because they don't need all the sales perspective. So they tend to not want to add the commercial perspective within PLM. Also, for many PLM tools out there, the variant management and the ways to write rules is not a focus area. It's not where they have really sort of put all their efforts to make that the best in class. You can always define the basic features, and you can write some text rules, but the tooling to work with these models are not very strong. And I'll show you some examples in a moment on what I mean by that. And the last point is that often there's a need to take the information that you build up in these models and be able to expose that in many different channels. So you might have a website where you have official information that you're going to sell, and you put that out for your global websites. But you can also imagine that there are other channels. You might have an internal sales application. You might have engineering applications where you get access to the information earlier because you need to work on the next year's product. And being able to create these different views is typically not possible with PLM. As I said, creating these models is at the center of what we do in Configit. And we have always believed that if you have to maintain this data, you have to be able to express the rules in a way that is meaningful for the people who have to maintain them. If you are forced to create rules in a particular syntax or in a particular way, because that's how the configurator works with them, then they become very hard to maintain because you cannot understand them when you come back to them a year later. So in ACE, we have numerous different rule editors, and allowing you to express rules in a way that has been turned out to be meaningful for the people who have to maintain them. The screenshot here is on one of these editors that allows you to define how an offering is of a product is presented in different markets. In many ways, the way to create these models is very similar to software development. You create these rules, and you have to make sure that they work, and you have to test them, and then you have to release them so that they can become consumed by whatever systems needs them. So we have adapted many of the same concepts as we know as a software company from software development. We have adapted those into ACE. And the first thing you need to do is you need to debug your rules. You need to understand when they do not behave as expected, why is that the case? And we have capabilities that allow you to ask that question and say, that's really weird. I don't understand why the sports pack is not available. There's a button you can click, and it will present to you an explanation in terms of what are the rules that together has the effect when you are in the particular state you're in, that particular choice is not possible. And now you can dig into those rules and start to understand what they say and fix them. We also have a testing capability in ACE. This allows you to run a test suite consisting of many tests. And you do so every time you do a change. So you can run some built-in tests. You can also run tests that you define yourself. And every time you do a change, before those changes are being released to downstream systems, you run all the tests and make sure that they all pass. When everything is passing, you have a pretty good assurance that you haven't broken something. And these rules are pretty tricky. You can do a little change in one corner and think that I've tested that little corner, but they are tied together in chains, and suddenly you cannot buy your products in France, and you don't notice that if you don't have a test framework that catches that up front. So those are some of the tools that any modeling application should expose to their users to make sure that the rules are right before they become released. when you start working on the feature level, some new possibilities opens up. And I think one of the more exciting ones is that you really can start doing complexity analysis based on features. So here's an example. It was presented by Audi some years ago at a German conference, the Smart Variant conference in Berlin. And they had worked with looking at a particular part. This is, I don't even know what it's called. It's the part sitting right behind the steering wheel. And depending on the choices you make for your car, there are different levers on this component. So if you have the lane assist, there's a lever for that. If you have adaptive cruise control, there's another control for that. And what they did was that they say, okay, so those are the variant drivers for this particular part. And now using the solution space export that we have in ACE, you can build up a tree of all the possible combinations of those controls, those features that control this particular part. And then what you do is that you can add, and you cannot read the thing on the right there, sorry, too small, but the point is you can then add probabilities of customers making those choices. And what you then can calculate is the probability of each of those variants of this particular part. And when you do that, you then start to get a picture, and I'm not going to go into the details, but the whole point is that you get a picture. And in this case, there were 96 different variants of this one part. And then you can start doing the statistics, and you'll find out that in this case, only a few of them were, in 80% of the cases, only 7 variants were being used. And there can be many reasons why you have 96. That might be the right number, but it might also be that you can save in terms of parts and other ways by reducing this number. And the way you reduce it is, well, you add some rules in the product model. You might say that you can only get lane assist on the big models, or that you group them together, that you can only get lane assist and adaptive cruise control at the same time. That will reduce the number of variants that you have to deal with. And this information you can feed directly from the configurator out to the engineers. So you can give them the Excel sheet with those 96 combinations and say, this is the number that you have to provide. So I want to just go through a couple of cases where I hope I can illustrate how introducing a CLM system will really help and benefit in engineering. The first case that I have brought with me today is from ThyssenKrupp Elevators. And ThyssenKrupp Elevators are, of course, making escalators and elevators. And this is a very much a technical engineer to order type product. In order to simplify the sales processes, they have used our ACE design automation plugin that was demonstrated and will be demonstrated also later today by Dennis. This is a plugin that allows you to create rules directly within the CAD environment the engineers are working in. So as the engineers are designing the product, they can also introduce the configuration parameters, the features and families, and link those families to the geometric aspects of the product or the materials of the product and other elements of the CAD environment. And then they can add also the technical rules. And once they've done that, we can take that product model, its features and rules, we can expose that out, put it on our ACE runtime environment, and we can use that configuration model. Maybe we add additional commercial rules on top of it, or we use them directly. We can use that in an application. It could be a CPQ application, a sales application, a website, whatnot, reseller application. We use that to allow the customer to configure the product. We might even visualize it in a nice 3D environment using the Unity plugin. And when the customer would like to have detailed drawings, because we do have this link from the configuration parameters to the CAD model that was the original, we can automatically generate the 2D or 3D CAD drawings based on the selections done within the configuration application. And this completely decouples the work done in the sales area from the work done by the engineers. The engineers, so to speak, will not be involved at all unless there are requests coming from customers that goes beyond what is allowed by the configurator. then that might trigger an ETO, an engineer to order process, where you will have to go back to engineering and get them involved and do the calculations whether that would be possible. So this is one example where engineers, by putting in the work up front, by adding the rules in the CAD environment, can basically fully get alignment with the sales cases and the sales processes without they have to be involved. The other example I have included today is from Volvo Bus. And Volvo is, of course, making buses, and they have traditionally been in a fairly high degree of ETO processes. So what they have done is that they have decided to keep their engineering rules in their PLM system. So they have already defined all the engineering rules, and they keep maintaining them within their PLM system. Then what we do is that we take those rules and we import them into our ACE application. And actually this was also demonstrated by Laura in her demo, which will also be repeated later today, how that can be done. They import those rules into ACE, they add the commercial rules within ACE, and then they have the single source of truth by compiling those two rule sets together as a single combined solution space. Once they've done that, they use that in their they use that in their sales application, and in that sales application, it's a little bit special because it has been set up, the configurator has been set up in a particular way so that it actually is possible to break the rules as you are configuring your product. And by breaking these rules, you are also then triggering an ETO process. So the rules actually you can break them so that the least important rules are being broken first. That's pretty unusual. Normally, when we do a configuration solution, you stay within what's possible. You stay within what the rule dictates is a valid configuration. But in this case, you can break the rules. If you do that, that will trigger a ETO process. A back office engineer will then be able to pick up that configuration. He will then be able to determine whether that is in fact a valid configuration. And if it is, he will add that to the set of valid configurations. So the next time around, if somebody should sort of get into the same configuration, it will already be allowed by the rules, and it will the next time around not trigger an ETO process. So this is again a way where you use the configuration engine to gradually move away from an ETO towards a CTO solution. As time goes, more and more of the combinations that gets requested are added to the configurator, and the special case, the ETO case, will be less and less common. So those were the two cases I had planned for today. In summary, I think the key benefits of introducing a strong configuration solution for engineering is that it eliminates errors, it allows products to be brought to market much faster, and part of the reason for that is that you can very efficiently reuse modeling data. On the right of this slide, I have copy-pasted from the presentation by Alec Crawford from JLR from last year, and I think it highlights some of these points quite well. They have eliminated configuration quality defects. They have 95% reduction in the product modeling time. That is a dramatic reduction in the amount of time they spent creating these product models. And that has meant that they no longer have that modeling on the critical path. Beforehand, this was really what limited how many different vehicle models, vehicle lines they could bring to the market. So having a tool that completely eliminates that from the critical path is what allows them to bring more products to market faster. And then we have these new capabilities of using the solution space reports to validate and optimize the product configurations that are being offered. So I think from an engineering perspective, engineers should embrace having a strong configuration solution because of these reasons. So that was what I had planned for today.